This is Michael Borenstein, and I'd like to invite you to register for my workshop on meta-analysis. You'll learn how to conduct a meta-analysis, how to report the results, and how to avoid common mistakes. But more importantly, you'll learn to think about meta-analysis in a whole new way. The workshop is divided into two parts. The basic course runs for the first half of June. The advanced course runs for the second half of June. Or you can register for both, which is called the intensive course. For a detailed list of topics, see the syllabus, which you can access below. Here, I wanted to give you a sense for the look and feel of the course. In the basic course, you'll learn how to decide what studies to include in the analysis, how to choose a statistical model, how to work with data in various formats, how to choose an effect size index, how to create a forest plot, how to estimate the mean effect, how to understand heterogeneity, how to write the results and discussion for publication, and how to avoid common mistakes in these areas. I'll explain each of these concepts and then work through a series of meta-analyses so we can see how the concepts are applied in practice. For example, here's the tocilizumab analysis. This is an analysis of 23 studies that enrolled patients who were hospitalized for COVID-19. In each study, some patients were treated with a drug called tocilizumab, and others were not. These are observational studies rather than RCTs. You'll learn how to choose a statistical model. In this case, we're using the random effects model. You'll learn how to choose an effect size index. In this case, we're using the risk difference. A risk difference to the left of 0 means that the treatment was associated with increased survival, and a risk difference to the right of 0 means that the treatment was associated with increased mortality. You'll learn how to estimate the mean effect. Here, the mean risk difference is 6 percentage points in favor of the drug. On average, patients who received the drug were 6 percentage points more likely to survive as compared with patients who did not receive the drug. In this plot, the mean is indicated by this vertical line, and this is bounded by a horizontal line that represents the confidence interval. The confidence interval is an index of precision and tells us how precisely we've estimated the mean. In 95% of cases, the true mean will fall between here and here. The confidence interval excludes 0, so we can conclude that the drug is associated with an increase in survival on average. Most meta-analyses focus on the mean effect size and its confidence interval, but this is not always the correct approach. That depends on how widely the effect size varies. If the true effect size is essentially the same in all studies, then indeed it would make sense to focus on the mean effect. However, if the true effect size varies substantially across studies, we need to focus also on the heterogeneity effects. The correct way to quantify the heterogeneity is to compute a prediction interval. In this case, the prediction interval looks like this. At one extreme, there will be some populations where the treatment is associated with a 30-point increase in survival. But at the other extreme, there will also be some populations where the treatment is associated with an 18-point increase in mortality. In a situation where the effect varies this widely, the mean is a poor way of summarizing the results. If we focus on the mean, which is 6 points in favor of the drug, we lose track of the fact that there are some studies where the true benefit may be substantially higher than that. And we also lose track of the fact that there are some studies where the treatment may be harmful. In the basic course, we learned how to quantify the heterogeneity. In the advanced course, we'll learn how to explore the reasons for the heterogeneity. To do that, we'll be using subgroup analysis and meta-regression. As we saw, there are some studies where the treatment is associated with benefit and others where it's associated with harm. In the advanced course, we will revisit this analysis and try to understand what factors are associated with this difference. The authors had hypothesized that the treatment's effect was related to the severity of the illness. We can use subgroup analysis to group the studies by severity. For patients who were moderately ill, the mean effect size is a 3-point increase in mortality, while for patients who were severely ill, the mean effect size is a 12-point increase in survival. It turns out that this difference is statistically significant and clinically important, and so the subgroup analysis appears to support the hypothesis. However, this could be due to a confound. For example, it's possible that these studies used a lower dose of the drug, while these used a higher dose, and that dosage, rather than the severity of the illness, is responsible for some or all of the difference between groups. To address this, we turn to meta-regression. We may be able to use meta-regression to assess the impact of severity while controlling for dosage. In the advanced course, you'll also learn how to work with complex data sets, such as studies that report data for more than one outcome or comparison, how to assess the potential impact of publication bias, to understand the limitations of the random effects model, what to do when the analysis includes only a small number of studies, and how to avoid common mistakes related to these issues. For a more detailed list, please see the syllabus, which is posted below. A part of every module will be to discuss common mistakes related to that module. This includes common mistakes related to choosing a statistical model, discussing heterogeneity, interpreting significance tests, assessing the potential impact of publication bias, and comparing subgroups. You'll also learn how to report the results in a paper. For each analysis, I'll provide a PDF of the results that can serve as a template for your own analyses. There will actually be two versions of this PDF, one intended for publication and a second version with annotations that explain, for example, why we chose one statistical model over another. The key elements for each module are the videos and the Zoom sessions. You'll have several days to watch the videos, and then we'll meet as a group to discuss by Zoom. We'll have at least 2 Zoom meetings a week, but I'm happy to schedule additional meetings as needed to accommodate people in various time zones. For those who cannot attend the meetings live, the meetings will be recorded and posted. You can also submit questions at any time on the discussion board. In the videos, we will work through a series of meta-analyses, starting with simple analyses and working our way up to more complex ones. I'll also provide you with data sets so that you can perform analyses on your own using step-by-step instructions as you do so. So that's an overview of what we'll cover in the workshop. But what I think is more important is the overall structure of the workshop. Many attendees tell me that the course stood out for being engaging and interesting as well as informative. I use real-world examples, and I choose examples that are compelling. We'll use some examples from COVID. We'll look at meta-analyses that companies have used as proof that their drugs were effective, and we'll discuss whether these claims were justified. To date, over 2,000 people have attended my workshops, either in person or online. Here is a testimonial from one of them, and additional testimonials are displayed below.
Constance J. Dallenberg of Alliant International University. As a professor of statistics, I was unsure whether to take the initial online course in meta-analysis, thinking that it might either be too dense and jargon-filled to be interesting, given Dr. Borenstein's impressive credentials and knowledge base, or too basic, given that I was already teaching a course. As I finish the series now, however, I am awestruck by the quality of this offering. Dr. Borenstein is quite simply a master teacher, so he offers complex material in a completely comprehensible form, the best of both worlds. I picked up details on the statistics, the use of CMA, and the theory behind the statistics, but I also, hopefully, will model the style and clarity of his teaching style in my own work in the future.
You might want to know something about me. I'm a co-author of the text, Introduction to Meta-Analysis. The first edition was published by Wiley in 2009 and became the best-selling text ever published on meta-analysis. The second edition was published in 2021. I'm the author of the text, Common Mistakes in Meta-Analysis and How to Avoid Them. I've contributed chapters to various books, including the Handbook of Research Synthesis and Meta-Analysis and Systematic Reviews in Health Research. I'm the author or a co-author of numerous papers on meta-analysis. I'm the primary developer of the software Comprehensive Meta-Analysis, or CMA, initially published in 2000 and now in its fourth major release. That software is used by tens of thousands of researchers throughout the world. I've served as the PI on numerous grants from the National Institutes of Health, the NIH, to develop methods and software for conducting and teaching meta-analysis. I'm a founding member of the Society for Research Synthesis Methodology and served as its president in 2017 to 2018. And I've been teaching these workshops since the year 2005, at workshops that are open to the public, at classes sponsored by universities and hospitals, and at the invitation of governmental institutions, including the NIH, the CDC, and the FDA. This course is being offered by the Columbia University School of Public Health as part of their episummer program. Click the episummer logo at the upper left corner of this page to visit their website and register for the course. If you have any questions, please feel free to contact me at this address. And thank you for taking the time to watch this video.